Today, we're tackling something huge, maybe the most fundamental yet least understood feature of our universe: gravity.
And it's one of those things we all think we know, right?
Exactly. So we've gone through the sources from Newtonian basics right through to general relativity, and our mission is really to give you the clearest conceptual path from gravity as a simple force to, well, to what it actually is.
The geometry of reality itself.
Yeah, let's unpack that.
For centuries, the starting point has been pretty simple. Gravity is, this fundamental interaction. It's all about mass and distance.
More mass, more pull.
More mass, more pull. Further away, weaker pull. And what you feel every day, your weight, is just the constant acceleration that force gives you.
Great, that basic pull makes sense for, an apple falling from a tree. But the way it works in space, that's where things get interesting. I mean, if gravity is just a straight pull, why doesn't the moon or, all our satellites just crash into the Earth?
That's the perfect question. And it's the first big conceptual jump we have to make.
So they're not just suspended up there.
Not at all. An orbiting object is in a constant state of falling.
Falling.
Perpetually falling.
Mm-hmm.
But sideways. See, an orbit is a perfect, precise speed. The object has enough forward momentum that as gravity pulls it down,
the Earth curves away from it.
Exactly. The surface of the planet drops away at the exact same rate the object is falling. So it just keeps missing. It's falling around the Earth.
That's a great way to put it, falling around something. But that still explains the motion. Newton's theory really struggled with the how.
Right.
How does the sun instantly influence Earth across 93 million miles of, nothing? That action at a distance problem.
Precisely. And that mystery is what led to Einstein and his incredible breakthrough.
The equivalence principle.
The equivalence principle, yeah. The core insight is that gravitational mass, how gravity affects you, is identical to inertial mass, which is just how much you resist being pushed or accelerated.
They're the same thing.
They're completely indistinguishable. And because of that, the feeling of gravity is exactly the same as the feeling of acceleration.
The old thought experiment. If you're in a windowless room, you can't tell if you're on Earth or in a rocket accelerating at 9.8 meters per second squared.
You literally can't.
Yeah.
And if they feel the same, they must be the same. So gravity can't be a force transmitted through space. It has to be a property of space and time itself.
So mass and energy, they don't just exist in space-time, they change it.
They mold it. General Relativity's core idea is that gravity is the curvature of space-time. Mass tells space-time how to curve.
And space-time tells mass how to move. So objects aren't being pulled. They're just following the straightest possible path.
The straightest path through a curved environment. We call it a geodesic.
That geodesic, okay.
Think of a plane flying the shortest route from New York to London.